Hello students, today I will start the fourth lesson about complex numbers. It has been delayed, but anyways, so in the syllabus of complex numbers you have AAHL 1.13 modulus and argument polar form. Z is equal to r cos theta plus I sin theta is equal to r cis theta. Euler's form says Z is equal to r into e raised to I theta. Some product and quotients in Cartesian, polar or Euler forms and their geometric interpretation. Okay. Then next part of the complex number AHL 1.14 says complex conjugate roots of quadratic and polynomial equations with real coefficients, right? De Moivre's theorem and its extension to rational exponents, powers and roots of complex number. Okay. The complex numbers, the sum of two squares, factorization, operations with complex numbers, equality of complex numbers, properties of complex conjugate, right? Okay. Any number of the form a plus bi or a plus b into iota, where a and b belongs to R and I is square root of -1 is called a complex number, right? Real and imaginary parts. In a complex number z is equal to a plus bi, a is the real part of z and b is the imaginary part of z, and we write them as rez and imz. Okay. So therefore, if this is the complex number z is equal to 2 plus 3i, then rez means the real part of z will be 2 from the complex number here, and imaginary part of z will be 3, which is here the 3 iota, means 3 into I. Okay, complex conjugate, right? Suppose z is a plus bi, where a and b belongs to R. The complex conjugate z is z star complex conjugate. Some books write z star, some books write z bar, okay, which is a minus bi. So here there was plus, okay, between real and imaginary part. So we change imaginary part to minus. We change the sign of the imaginary part. Real part we keep as it is, okay. So real part of z conjugate is same as real part of z, and imaginary part of z conjugate is negative of imaginary part of z, okay. And there are some properties: addition, subtraction and multiplication. So addition means we add the real parts and we add the imaginary parts together. Similarly, we subtract the real part separately and we subtract the imaginary part separately. Multiplication will be as we do in algebraic expressions, same way we have to multiply them, a into c, then a into di will be this, then b into ci, so will be this, and then b into di square, which will be this. Okay. Two complex numbers are equal if their real parts are equal and if their imaginary parts are equal. This is simple thing. Modulus of a complex number, if z is equal to a plus bi, okay, then the modulus is actually the length of the vector ab, okay. You can draw a complex number on the complex plane like vectors, okay. So it is like a column vector ab, and the real number, this vector has a magnitude, okay, which is modulus of a complex number is square root of a square plus b square. So as we find the magnitude of a vector, like that we find the modulus of a complex number, okay. Now properties of modulus. Modulus of z conjugate is same as modulus of z. Modulus of z square is same as z into z conjugate. Modulus of z into z2 is same as modulus of z1 multiplied by modulus of z2. Then modulus of z1 divided by z2 is same as the modulus of z1 divided by the modulus of z2, okay, where z2 is not equal to 0, of course. Then in the same way we can write Modulus of Z1 into Z2 into Z3 into Zn is same as modulus of Z1, modulus of Z2, modulus of Z3, so on, modulus of Zn. Okay. So, we can also write modulus of Z to the power n is equal to modulus of Z and that to the power n, right, where n belongs to Z plus, of course, the positive integer. Okay. So, from this you can understand that if you have 2 plus 3 iota or 2 plus 3 I and 3 plus 4 I, then we can add them like this. The real parts will be added together plus the imaginary parts will be added together. 2 and 3 5 plus 4 plus 3 7 I. This will be their addition. In the same way you can subtract, and in the same way you can divide also. If you have to subtract, here will be minus sign, here will be minus sign, and here will be minus sign, right. But this will change, of course, this and this both will change. So, if you have to write minus, if you have to subtract them, then you will get, let me change this, 1 minute, because minus of them will not be that, it will be equal to 2 minus 3 minus 1 and 3 minus 4 minus 1 iota. So, minus 1 minus I will be their subtraction. So, if you subtract them, so this will be the answer, right? Yeah. Okay. Okay. Now, the complex, in the second part, there are two parts in this book. Chapter 4 is also about complex number in the green book, book 2, and chapter 14 is also on the complex numbers. Okay. So, in the second part, the complex plane is there, modulus and argument is there, geometry in the complex plane is there, polar form, Euler's form, De Moivre's theorem, and roots of a complex number. Okay. Okay. So, on a complex plane or argand plane, we take the real axis in place of x axis, and we take the imaginary axis in place of the y axis, right. So, all the real numbers, all the real parts of a complex number will be expressed like we express x, and all the imaginary parts of complex number will be expressed as we express y, okay, the y coordinate. Okay. So, argument of a complex number. So, if you have a complex number, then it is better to draw the graph of it and then locate that complex number on the graph. It will have the same sign conventions which are there in the coordinate system, plus x and y plus plus, sorry, let me show you here. Plus plus, minus plus, minus minus, and plus minus. Okay. These will be the sign of real and the imaginary parts. Okay. So, you can take the same sign conventions which we take in the coordinate system. Now, if your complex number is both parts positive, a plus b iota or a plus bi, then it will be in the first quadrant. Okay. Then the angle formed by this vector, as I told you earlier, a complex number can be represented by a column vector which will be a and b, which is in the first quadrant. So, which will be a vector starting from origin until p. Okay. So, this vector has, suppose this is the angle theta with the x axis, then the opposite of theta is b, adjacent of theta is a, and you can represent it by tan inverse. Argument of z is tan inverse of b by a, where this angle, okay, this will be in radian form, and this angle is between minus pi and plus pi, but minus pi is not included, plus pi is included. So, if your answer is more than positive pi, you have to subtract it from 2 pi, or if your answer is more than negative pi, sorry, less than negative pi, then you have to add 2 pi to it. Okay. What I mean, because for example, suppose you have an answer here. Okay. So if you write answer from this side, that will be wrong. Okay, because it cannot cross pi. Okay, it is only up to pi. Okay, so therefore to measure this angle you have to come in the clockwise direction like this, and that will be a negative answer, negative angle, right? The argument will be negative. Similarly, if you are here in the fourth quadrant, and if you come like this is a wrong way to calculate, to measure the argument of a complex number. You have to come in the negative direction, clockwise direction, and it will be a negative angle, right? Similarly, if you want to measure an angle, negative angle, if it is here, your complex number is here, you cannot calculate like this. This will be a wrong thing. It should be like this. Okay. This will be correct direction, this will be wrong direction, because it will cross minus pi, whereas it should not cross minus pi. It should be more than minus pi and less than plus pi. So I hope you will remember this. Okay. Then geometry of complex number. Distance between 2 points which are represented by the complex numbers in the complex plane. So suppose P1 is one complex number, P2 is another complex number, then distance between P1 and P2 will be given by P2 minus P1. You can see arrow mark over it because it can be treated like vectors. So as we do in vectors, so PO one vector plus OP second vector. Okay, PO will be first vector, OP will be second vector, OP1, sorry. P2O, okay, let me correct, P2, P1 is equal to P2O plus OP1, okay, P2O plus OP1, OP1, see, OP2 is one vector Z2, OP1 is second vector, I mean first vector Z1, second vector is Z2, OP1, OP2, then P2 P1 will be P2O plus OP1. P2O is in the negative direction of Z2, therefore it will be minus Z2, and OP1 is in the right direction, so plus Z1, therefore it will be Z1 minus Z2. And the modulus of Z1 minus Z2 will be the magnitude of the vector P2 P1, which will be the distance between P1 and P2. Okay. So if Z1 is OP1 and Z2 is vector OP2, then magnitude or modulus of Z1 minus Z2 is the distance between P1 and P2. So we treat them like vectors, right? We treat them like vectors for the direction and for the finding the distance, right? Okay. Next part, midpoint. So like coordinate system, in vector, in complex numbers also, the midpoint will be add both the complex number, divide by 2. Okay. So OR is OR is the addition of complex number OP and OQ, which are Z and W or W and Z. Then their midpoint will be here, which will be represented by OP, and it will be W plus Z divided by 2. Okay, W plus Z divided by 2. Okay. Transformation. Yeah, like we do transformation in geometry, okay, or in vectors. There are transformations in functions and vectors also. There can be transformation like that. We have transformation in complex numbers also. Okay. So here I have shown one transformation of the complex number. Suppose we have a complex number Z is equal to X plus IY, then I into Z will be I into X plus IY. When we open the bracket, we get IX plus I square Y. I square is negative 1, so negative Y plus IX. Okay. So negative Y plus IX will be transformed here. Okay. The complex number was here, PXY means X plus y iota y. Now it will become minus y plus iota x. Okay. So it has been transformed by 90 degrees anti-clockwise, right? And modulus of z will be square root of x square plus y square, and modulus of iz will also be square root of x square plus y square, because from this complex number minus y square will be y square and plus x square will remain x square. Okay. Now polar form. Polar form means representing a complex number with the argument. Okay. Modulus and argument form. So if a complex number has x coordinate is like this, z is equal to a plus bi, here is that complex number. Okay, then look here, we can draw a perpendicular here, this is b, this is a, okay, and this is r, we can take the length of the vector op. Then look here, from this triangle we can write cos theta is equal to b by r cos theta, b by r, a by r is cos theta. So a is r cos theta. So therefore the real part of the complex number will be r cos theta. Similarly the imaginary part will be r sin theta, right? And then from this we can say that r is representing the modulus of complex number, theta is representing the argument of the complex number z. Then we write in polar form cis theta. Cis theta is short form for cos theta plus I sin theta. Okay. So z will be modulus of z and cis theta. Okay. So that will be in the polar form, right? So this is called modulus argument form, because we are writing modulus here, we are writing argument theta, okay, there. Okay, polar form is very helpful in dealing with multiplication and division of complex numbers, right? Now conjugate of a complex number will have the negative argument, okay. So if z is modulus of z into cis theta, then z conjugate will be modulus of z, same modulus, but cis theta will be negative theta, okay, cis of negative theta. So if you have a complex number here in the first quadrant, then its conjugate will be in the third quadrant. So actually any complex number is reflected in the real axis to get its conjugate, okay, that is the rule. Okay, properties of cis theta. The useful properties of cis theta are cis theta into cis phi will be cis phi theta plus phi, cis theta over cis phi will be cis theta minus phi, and cis theta plus k2 pi is same as cis theta. Why this is same? Because we know that cos theta has period 2 pi. So cos theta can be represented by cos of theta plus any multiple of 2 pi. So k2 pi, and sin theta is also having period 2 pi, therefore sin theta can be represented as sin theta plus k times 2 pi. Okay. So therefore any complex number cis theta plus k into 2 pi is same as cis theta, right? Okay. Now multiplication of complex numbers in the polar form, of course. So if z is modulus of z is cis theta and w is modulus of w cis phi, then z into w will be z modulus of z cis theta multiplied by modulus of w cis phi, and we multiply both the moduli and we add the argument of them, cis theta plus phi, right? So therefore modulus of z1 z2 is same as modulus of z1 into modulus of w. Sorry, I said z1 z2. It is modulus of z into w is same as modulus of z multiplied by modulus of w, right? Okay, look at this question, right? This is the first question I have taken from the past papers, right? So, see this question, it says the complex number w and z satisfy the equation z upon w is equal to I, conjugate of z plus 2z, conjugate of w plus 2z is 4 plus 5i. Find w and z in the form a plus bi, where a and b are real are integers. Okay. So, look here, from this equation what we can write? Z is equal to I into w, and now therefore w conjugate plus 2z, which is to be found, will be w conjugate, and this will be 4 plus 5i. Okay. Now z is iw, right? So therefore this is equation 1. Now let w is equal to x plus yi, right? So therefore z will become I into x plus yi, which will be xi plus yi square, and I square is negative 1, so minus y plus xi. This will be the value of z. Okay. So therefore in equation 1 will be, see, equation 1 was w conjugate plus 2z. So w conjugate plus 2z, right? W conjugate plus 2z is 4 plus 5i. I am writing that equation, 4 plus 5i. Now I will substitute the value of w conjugate in terms of x and y. W conjugate will be x minus yi. Let me write that here itself. The w conjugate is x minus yi. You know already about it. So therefore w conjugate will become x minus yi plus 2 times z. Z we already found, minus y. Look here, minus y plus xi. 2 minus y plus xi. So 2 times minus y plus xi, which is 4 plus 5i. Open the bracket. So x, this real part with this real part will be x minus 2y, and the imaginary part, this is imaginary part with this imaginary part, will be plus of 2x, okay, minus y iota, or I is equal to 4 plus 5i. I hope you understand this, right? Now comparing real and imaginary parts, comparing real and imaginary parts, we have, see, the real part will be equal to the real part and the imaginary part will be equal to the imaginary part. So therefore x minus 2y is 4 and the imaginary part 2x minus y is 5. Okay, we get these two equations, number 2 and number 3. Let me write, right? So solving 2 and 3, let me make it little smaller, sorry. Yeah, I wanted a space. Now solving 2 and 3, we have, you know how to solve them. So you can use substitution method or elimination method. So we will get x is equal to 2, right, and y is equal to minus 1, right. So therefore what we wanted here, find w and z in the polar form, in the form a plus bi. So therefore this implies z was what we had taken, w was x plus yi. So first I will write w is equal to x plus yi. So x is 2, y is minus 1i. So w is 2 minus I, and z was this, right, minus y plus xi, and z will be minus y. So minus of minus will become plus, right, 1, and plus xi, which will be 2i, right. So this will be the value of w and z. This was asked in this question, of course. So this is the solution, right. This is no use of this page. Then let us go to Euler form, okay, Euler's form also you can call it. So for any theta belongs to R, e raised to I theta is cos theta plus I sin theta. This is called Euler's form or Euler's form, you can say. This identity allows us to write any complex number z is equal to modulus of z into cis theta in the Euler form as z is equal to modulus of z. So modulus of z will remain in its own, in the same place. Instead of cis theta we will write e raised to I theta, right. So for example, if you have a complex number z is equal to 1 plus I, then modulus of z is root 2, you know it, square root of 1 square plus 1 square, which will be root 2, and theta will be from this figure you can say opposite over adjacent will be tan inverse. So tan inverse 1 over 1, which will be pi by 4. So theta is pi by 4. Therefore 1 plus I will be root 2 cis pi by 4, and hence in Euler form we can write root 2 e raised to I into pi by 4, okay. So root 2 cis pi by 4 is in polar form of this complex number, and root 2 into e raised to iota pi by 4 is in Euler form of 1 plus I, right. Now the question says here minus 1 plus I, write minus 1 plus I in polar form and Euler form. So it is very simple. Let us denote it by z or z1. So let z1 is minus 1 plus I. Therefore modulus of z1 will be square root of 2. You know it, how to find, and argument of z1 will be, this is in the second quadrant, right, it is in the second quadrant. So I can show you here, in the second quadrant this will be pi by 4, because negative 1, tan inverse of negative 1 will be pi by 4, but we write in the second quadrant pi minus pi by 4, so 3 pi by 4. So we have the modulus, we have the argument. So therefore in Euler form z1 will be root 2 e raised to iota into or I into 3 pi by 4, okay. This is the Euler form. So I hope you understand this. Also they wanted a polar form, so let me pull it little bit down, because first they wanted the polar form and then the Euler form. So in polar form z1 will be root 2 cis 3 pi by 4, that's it, okay. So in polar form we have it root 2 into cis 3 pi by 4, and in Euler form we have z1 is equal to root 2 into e raised to I 3 pi by 4, right. Okay, second part, yeah, there is second part on the next page. So let z2 3 cis negative pi by 6. This we have to write in Cartesian form and in Euler form. Okay. So z2, we know that z2 is r into cos theta plus I sin theta, right, because we have the angle. R we already have 3. So 3 cos of negative pi by 6 plus I into sine of negative pi by 6. We know that cos of negative pi by 6 will be positive pi by 6, which will be root 3 by 2, and this negative sign will come out. Okay. So therefore minus I into pi by 6 is 30, which will be half, right. So when we multiply, we get 3 root 2 by 2 minus 3 by 2 I. Okay. This is Cartesian form. Now Euler form is also required here. So we can directly write, because we already have theta. So and z2 is equal to 3 e raised to I into negative pi by 6. That's it. We can write it directly if theta is given, right. So this is in Euler form. Okay. Now the third part, I hope you will do the third part. I will keep this third part on the next page for you. So this is like homework. I hope you can do this, right. Okay. Here it was already. So okay, anyway, homework. Now next section is De Moivre's theorem. So De Moivre's theorem says, if you have a complex number z is equal to modulus of z cis theta, then z square is modulus of z cis theta into modulus of z cis theta, which will be modulus of z square cis theta plus theta. See, we multiply the modulus and we add the arguments, like logarithmic rules, right. Multiplication changes to addition and division changes to subtraction. The same way we write it here. So z into z will be modulus of z square cis theta plus theta, because there was multiplication of cis theta into cis theta. So it will become modulus of z square into cis 2 theta. Similarly, z cube will be z square into z square we already have here. So modulus of z square into cis 2 theta multiplied by modulus of z into cis theta. So moduli will get multiplied. So z modulus of z to the power 3 or cube of it, cis 2 theta plus theta, which will be cis 3 theta. So in general, De Moivre's theorem says modulus of z cis theta bracket to the power n will become modulus of z to the power n into cis n theta, where n belongs to q. I think this should have been n belongs to z, because there is only this solution when it is z, n belongs to z. If it is a rational number, then you will have it in different form. It will be modulus of z to the power n cis theta plus 2k pi, right. Okay, or theta plus 2k pi divided by n. It will be like that. Okay, is that clear to you? But anyway, we are going to see it later on. So this is the form, right. This is in the by de Moivre's theorem. Okay, let us solve one past paper question based on it. Okay, so the question says, consider the complex number z is equal to w1 over w2, where w1 is root 2 plus root 6i and w2 is 3 plus root 2i. Express w1 w2 in the modulus argument form and write down the modulus of z and the argument of z, right? So first part says we have to write each one of them, w1 and w2, in modulus and argument form, right? So w1 is root 2 plus root 6i, therefore modulus of w1 will be square root of 2 plus 6, 8, which will be 2 root 2, right? And argument of w1 will be tan inverse 6 by 2, okay, which will be tan inverse root 6 by root 2, which will be root 3, and root 3 will be pi by 3. So this will be pi by 3, right? And w2 is, or first let us write w1 and w2 in the modulus and argument form. So let me write this also, 3 plus root 3i. So modulus of w2 will be square root of 3 square 9, 9 plus 3 12, 12 will be 4 times 3 12, so 2 root 3, and argument of w2 will be root 3 by 3, which will be 1 upon root 3, means pi by 6, right? So these are the modulus and argument of w1 and w2. So therefore I can write the modulus of z, because z is w1 divided by w2. So let me write it here on the next page, part 1. Z is w1 divided by w2. So therefore modulus of z will be modulus of w1 by w2, like this, and we know that it is modulus of w1 divided by modulus of w2, and this will be 2 root 2 divided by 2 root 3, okay. So root of 2 by 3 we can write, right? Root 2 by root 3, which can be root 6 by 3, no problem, we can write the modulus like this. And argument of the second part is for the argument, so let me highlight this. They wanted the modulus, and second part, argument of z will be argument of w1 divided by w2, okay. So which will be argument of let me move it little bit here, yeah. So argument of w1 minus argument of w2, right? So I already have argument of w1 and w2, pi by 3 and pi by 6. So pi by 3 minus pi by 6. So LCM is 6. So 2 pi minus pi, pi by 6. Okay. So therefore argument of z is pi by 6, right? Okay. So we wrote both the parts. Now B part says, B part is there space, I don't have space, so I will need space. Wait, let me copy empty page here. Yeah, now I have space. Now B part says, what we have to find? Find the smallest positive integer value of n such that z to the power n is a real number, right? See, it will be a real number if the argument is if you want it to be a real number, then the imaginary part should be 0, right? It means sin theta should be 0, okay, in the modulus argument form, cis theta cos theta plus I sin theta. So sin theta should be 0. So sin theta will be 0 when theta is multiple of k pi, okay, because sin pi we know 0, so k pi can be the multiple of it. So therefore nth power of z is a real number, yeah, because z to the power n is a real number, that is z to the power n is a real number if the argument of z is some multiple of pi, k pi, where k belongs to z, is an integer, right? Okay. So what is argument of z? But this should be argument of z to the power n, and we know that argument of z to the power n becomes n into argument of z, which should be equal to k into pi. So n into argument of z, what is argument of z? Pi by 6. So n into pi by 6 is k pi, pi gets cancelled, and k will be an integer if n is equal to 6, because look here, if this becomes 6, then 6 and 6 cancel and k will be an integer, right? So therefore this implies n is equal to 6, okay. This is the smallest positive integer, okay, is smallest positive integer. Okay. Let us see the next part. Yeah, the next part says roots of complex number. This is also important part. So z to the power n, solving z to the power n is equal to c. Consider an equation of the form z to the power n is equal to c, where n is the positive integer and c is a complex number. So therefore the nth root of a complex number c are the n solutions of z to the power n is equal to c. There will be n solutions. So nth root will have n solutions, third root will have 3 solutions, fourth root will have 4 solutions, fifth root will have 5 solutions, and so on, right? So if fourth root we have to find of 2i, then 4 solutions of z to the power 4 is equal to 2i. There are now there are exactly n nth roots of c. I mean there will be n nth roots, whatever is nth root, third root, fourth root, fifth root. So 3, 4 or 5 roots will be there, okay. Then if c belongs to R, the complex roots must occur in conjugate pair, okay. If c is a real number, then complex roots must be in conjugate pairs. So if one root is 2 plus I, the other root should be 2 minus I. If one root is 1 plus 3i, the other root should be 1 minus 3i, and so on. And if c is not a real number, then the complex roots do not all occur in the conjugate form. So I hope you understand. Maybe there is one complex root and the other conjugate is not its root, like that it will be. The roots of z to the power n will all have the same modulus, which is modulus of c to the power 1 by n, or 1 nth root of modulus of c, okay. On an Argand diagram, the roots will lie on the circle with radius modulus of z to the power 1 by n, means the modulus of that nth root will become the radius of the circle with center at the origin, okay. and all the roots will lie on that circle, and those roots are equally spaced. Look here, equally spaced around the circle. So if this is real and imaginary axis, then if one root is there, second root is here, the third root is here, they are equally spaced, right? So they are equally spaced, all the roots are equally spaced. So they also form, if you join the vertices of all the complex numbers on the circle, then they will form a regular polygon, right? So if you join the points corresponding to the roots on the circle, you will obtain a regular polygon. Okay, so let us solve some questions based on finding the roots. Now this is very famous question, 3 cube roots of unity. You all know about it, right? Now they want it in two ways, factorization method and nth root method, right? So we will start with the factorization method. So let z cube is equal to 1, because we want 3 cube roots of 1. So therefore z to the power 3 minus 1 to the power 3 is 0. Now you already know the formula a cube minus b cube, which is equal to a minus b, second bracket, a square plus ab plus b square. Okay, I hope you remember this formula. So using that formula, I will write two factors of it, z minus 1, z square plus z plus 1 is equal to 0. So first factor z is minus 1 is equal to 0 gives me one answer, z is equal to 1. The second factor z square plus z plus 1 is equal to 0 will give me the complex roots. So this will give me z is equal to a, b and c minus b plus minus under root of b square minus 4ac over 2a. So minus b, so look here, this is a, this is b, this is c. So minus b plus minus under root of b square minus 4ac divided by 2a. This formula I am going to use. So minus 1 plus minus under root of b square, 1 square is 1, minus 4 times a and c both are 1, divided by 2a, a is 1, 2 into 1. So therefore z is equal to minus 1 plus minus, this will be negative root 3, right? Minus 1 plus minus negative root 3 by 2. So negative root 3 will be root 3i over 2. So therefore z is equal to 1 and z is equal to minus 1 plus root 3i by 2 and z is equal to minus 1 minus root 3i by 2. These are the 3 cube roots of unity, or 3 cube roots of unity. Now in the second case they want the nth root method. By nth root method we have to find it. So I will do it on the next page, nth root method. Okay. So nth root method means what we have learned just now. In the nth root method, z cube is equal to 1 we will write, right. Now this in modulus and argument form will be 1 into sys 0, right. But because we want cube roots, so 0 plus k 2 pi or 2 into k pi, whatever way you want to write, where k belongs to z, right, in the polar form. Okay. Now therefore z will become, we will take the cube root on both the sides. So 1 into sys 0 plus k 2 pi bracket to the power 1 by 3. So z will be 1 to the power 1 by 3 and sys will get this multiplied. Okay. So 0 plus k into 2 pi by 3 in the angle, it will get multiplied in the angle. So therefore z is equal to 1 sys k into 2 pi by 3, right. So for k is equal to 1, we start with 0, k is equal to 0, we get 3 cube roots. So z1 will be 1 cis 0, cis 0 is 1, so 1 will be the first answer. Then k is equal to 2, k is equal to 1, sorry, z2 will be, replace k by 1, so 1 cis 2 pi by 3, 2 pi by 3 is in the second quadrant, so in the second quadrant the real part will be negative because cos 2 pi by 3 will be negative half and sin 2 pi by 3 will be positive root 3 by 2. So root 3 by 2 I, okay, second root, and k is equal to 3, 2, third root will be z1, z2, z3, 1 says, now replace k here, replace k by 2, 2 to the 4 by 3, so cis 4 pi by 3. 4 by pi by 3 is also in the second quadrant, in the third quadrant, 4 pi by 3. So it will be in the fourth quadrant, cos 4 pi by 3 will be negative 1 by 2 and sin 4 pi by 3 will be negative root 3 by 2. So negative half negative root 3 by 2 I. So these are the 3 cube roots of unity, right, same 3 cube roots what we got here, okay. So are the cube roots of unity. Let me make it little smaller. Are 3 cube roots of unity. Okay. Now next question is again solve the following equations and display the solution for each on the Argand diagram. We have to show them on the Argand diagram, right? Okay. So first one is z cube is equal to 2 plus 2 iota, 2 plus 2 I, okay. Now look here, what is the modulus of this? Modulus of z, let me write it in the modulus and argument form first, okay. So this will be square root of 2 square plus 2 square, 4 and 4 8, so 2 root 2. Says it will be 1 tan inverse 1 which will be pi by 4 in the first quadrant. So pi by 4 plus k into 2 pi, we always write it like that, where k belongs to z. So therefore z will be the cube root of the whole thing, cis pi by 4 plus k into 2 pi to the power 1 by 3. So modulus will have the same power, 2 root 2 to the power 1 by 3, and cis will have angle will be multiplied by 1 by 3. So therefore it will go in the denominator. So pi by 12 4 times 3 and plus k into 2 pi by 3, okay. Okay, so this will be 2 root 2 cube root of 2 root 2 is root 2, and says I will write same denominator for both of them, pi by 12 plus I will multiply by 4, so k into 8 pi by 12, right, so that both the denominators are same. So now when for k is equal to minus 1, look here, you could have taken k is equal to 0, 1, 2, 3. I am taking minus 1 so that I get the correct argument between minus pi and plus pi, okay. So when I take k is equal to minus 1, my first root z1 will be root 2 cis, I will replace k by minus 1, so pi minus 8 pi, okay, pi minus 8 pi will be 7 pi, minus 7 pi, right, minus 7 pi by 12 then k is equal to 0, second root will be z2 root 2 sys. Now I will replace k by 0. When k is replaced by 0, I will get pi by 12 because this part will become 0. So sys pi by 12. In this I am substituting each time, and when k is equal to 1, z3 the third root will be root 2 sys. Now look here, I am going to replace k by 1, so k will be replaced by 1. So pi by 12 plus 8 pi by 12 will be 9 pi by 12, which will be 3 pi by 4, right? So sys 3 pi by 4. These are the three roots, okay, and they said display them on the Argand diagram. Anyway, I will display them here. Real and imaginary axis I will draw, right? Okay, then I will draw a circle. Let me extend this. Okay, this is real axis, this is imaginary axis. Okay, now this way these three roots, see negative 7 pi by 12 will be somewhere here, right? Let me redraw. Yeah, it will be somewhere here. So z1 I will represent only by z1 because I already have. Then root 2 sys pi by 12 will be in the first quadrant. So will be something like this. z2, I mean I can represent z1, z2, z3 in any order, but no problem. And the third one will be here z3. So actually I should write z1 here, z2 here and z3 here, right? So let me replace z2 by 1, z1. Okay, so I will write here z1 and z1 will be z3. So let me write here z3 and z3 will be z2, right? Now they are correct. So now I can write z1, z2, z3 in the correct order. z1, z2, z3, right? Origin. As I said, they are equally spaced, right? So this was part A. In the same way, you have to find part B. So let me copy that part B, and the third one I will keep for you. Okay. So z cube is minus 2 plus 2i. So modulus, let me write it in modulus and argument form. So modulus of z cube will be square root of 2 square 4 plus 4 8, which will be 2 root 2, right? And argument of z cube will be, it is in the second quadrant, minus 1, so means pi by it will be pi by 4 in the second quadrant, okay, because look here, this is in the second quadrant, negative real part and positive imaginary part. So here is pi by 4, so therefore this angle will be pi minus pi by 4, 3 pi by 4, okay. So argument will be 3 pi by 4, but we write, because we are finding the cube roots, so therefore z cube in the modulus and argument form will be like this, sys 3 pi by 4 plus k into 2 pi. Always we use k into 2 pi because k gives us different roots, right? So we have to write that. Now taking the cube root, so z is equal to 2 root 2 cis 3 pi by 4 plus k into 2 pi, all of them to the power 1 by 3. So modulus to the power 1 by 3, and argument will get multiplied by 1 by 3, so it will go in the denominator. So 3 pi by 12 plus k into 2 pi by 3, because 4 times 3. So z will be root 2 and cis 3 pi by 12, and here also I will take 12, so multiply by 4, so k into 8 pi by 12, right? This is by De Moivre's rule. Okay. Now we will again take them as we took earlier, right? So do I have space? Yeah, so this I will move, yeah, B part I will keep for the homework. I mean I am doing, yeah, B part was copied here. So anyway, I am already doing this B part. See, I wrote here z is equal to, so I will write here root 2 cis 3 pi by 12 plus k into 8 pi by 12. So for k is equal to minus 1 root, k is equal to 0 second root, k is equal to 2 third root. Sorry, 1 not 2. Okay. So I will replace k here by 0, by minus 1. So I am going to get z1 first root, root 2 cis minus 1 means 3 pi minus 8 pi by 12, which will be root 2 cis 3 minus 8 minus 5 pi by 12, z2 root 2 cis, z2 means when we replace k by 0, so 0 will give you 3 pi by 12, 3 pi by 12 will be pi by 4, right, and z3 root 2 cis, here when I replace k by 1 here, so 3 and 8 11 pi by 12. Okay, when I want to show them on Argand plane or the complex plane, okay, this is a real axis, this is imaginary axis, and the three complex numbers. The negative one will be in the fourth quadrant, somewhere minus 5 pi by 12, okay, somewhere here, root 2 cis minus 5 pi by 12. The next one, pi by 4, of course will be in the first quadrant, root 2 cis pi by 4, and the third one 11 pi by 12 will be somewhere here, okay, they should be equally spaced, so let me move this here, yeah, now they are correct. So root 2 cis 11 pi by 12, okay. So I hope you understood, they are equally spaced, you have to show them properly on the Argand diagram. The next part I will keep for the homework for you. You can try part C. I will copy it on the third page. Homework. Okay. One last question which is from past paper, right? May 2023. Okay, this question is from May 2023. Do not write on this page. It says maximum marks 22. See, this is 22 marks question. Consider the complex number u is equal to -1 plus root 3i. Okay. Now, part A says, by finding the modulus and argument of u, show that u is equal to 2 into this. Okay. So I have already copied this part. So what I have to show? Modulus and argument. By finding modulus and argument, I have to show that u is in Euler form. U is equal to 2 into e raised to I into 2 pi by 3. Okay. So I will find the modulus of this complex number, which will be square root of 1 square 1, 3 root 3 square 3. So 4 means 2. Okay. This is the modulus and argument of u. Argument of u will be tan inverse root 3 by minus 1. So real part is negative, so it means it is in the second quadrant. So in the second quadrant, pi by 3, which will be pi minus pi by 3, 2 pi by 3. Okay. So this is argument of u is equal to 2 pi by 3, right? Okay. So therefore now u will be modulus of u into e raised to I argument of u, right? This is the Euler form. So therefore u will be 2 e raised to I 2 pi by 3. This is the final answer for 2 into Euler form. I mean, in the Euler form you have to write it like this. It was for 3 marks. This is not difficult part. Okay. So I hope you had done this part. Now B part says, find the smallest positive integer n such that u to the power n is a real number. U to the power n is a real number. Okay. U to the power n is a real number. Now it will be a real number if sin theta will become 0, isn't it? In cis theta, cos theta should be some real number and sin theta should become 0. So therefore argument of u to the power n must be k pi, where k belongs to z, some integer z, right? So therefore argument we have already found here. So u to the power n will have argument I into 2 pi n by 3, 2 pi by 3 n. Okay. From part A, two pi by 3 n will be equal to k pi, isn't it? See here, u is this, so u to the power n, let me write here, u to the power n will be 2 to the power n, and this will get multiplied by n, e to the power I 2 pi by 3 n. Okay, like this you get in the Euler form. De Moivre's theorem, of course, we apply. Okay, now it will be, this k will be an integer when this 3 gets cancelled. So this will get cancelled with n 3 only, and they wanted smallest positive value, isn't it? Smallest positive integer n. So it will be 3 only. So therefore this implies n is equal to 3. I hope you understood. Because when n is 3, 3 and 3 will get cancelled. See here, if n is 3, 3 and 3 get cancelled. So k will become 2. It will be an integer, and 2 pi or only pi will make sin theta 0. Okay. So this is the smallest positive value of n. This was the first part. Second part says, find the value of u to the power n when n takes the value found in part B1. Means when n is this value, we have to find the value of u to the power n. So we already wrote here u to the power n. So u to the power n will become 2 to the power 3, okay, n means 3 because n is 3, and e to the power I 2 pi by 3 into 3, n is 3, right? This 3 and 3 goes, 2 to the power 3 e raised to I into 2 pi. So this will be only 2 to the power 3 because e raised to I 2 pi will become 1, right? Cos 2 pi and sin 2 pi will be, let me write otherwise if you want in the polar form. This will be 2 cube 8 cos of 2 pi plus I sin of 2 pi. Now sin 2 pi is 0, cos 2 pi is 1, so it will be 8. So therefore u3 is 8, okay. u3 means u to the power n, right? Consider the equation z to the power 3 z cube plus 5z square plus 10z plus 12 is equal to 0, where z belongs to C. Z is a complex number, okay. First part says, given that u is a root of this equation, find the other roots. So u is a root, right? So we will start with this. Since u is equal to, what was u? Let me write that. Minus 1 plus root 3i. See, here it is u. Minus 1 plus root 3i. Okay, is a root. Therefore, other root is conjugate of this, isn't it? Whenever there is a complex root of a equation, of a complex equation, then always there will be a complex conjugate root. So other root is minus 1 minus root 3i, because we change the sign of the imaginary part. Real part we keep the same. So other root is this. This is the second root, okay. Now we have to find the third root also. So let z cube be the third root. This is 9 marks question. Z3. So therefore, now look here. Sum of the roots. Sum of the roots will be minus n minus 1 over a n, isn't it? A n minus 1 over a n. This you must have learnt it, finding the sum of the roots and the product of the roots. This is by Vita's equation, right? So I hope you know the Vita's equation. From Vita's equation, this will be the root, and a n minus 1. Look here, this is a n, this is a n minus 1. So a n minus 1 is 5, so minus 5, and a n is 1. So therefore, sum of the roots is minus 5, right? And therefore we will write all the roots. So first root is minus 1 plus root 3i. Second root we already found, this shaded one, minus 1 minus root 3i, and third root we have taken at z3 is equal to minus 5. In this and this gets cancelled. This and this will get added, negative 2 plus z cube is minus 5. So therefore, z3 will be minus 5 plus 2 minus 3, okay. So the third root is this. Therefore, there is no space. Let me take this up, little up I will take it. Yeah. Therefore, the roots are minus 1 plus root 3i, this was given. The conjugate we found, and minus 3. These are the 3 cube roots. 3 roots of the given equation, right? Okay. Now second part says, by suitable transformation from z to w, or otherwise find the roots of the equation 1 plus 5w plus 10w square plus 12w cube. Now look here, let me write that equation which we had. Yeah. See, since in the roots of this equation the following equation are, see, we have three roots here I wrote, okay. So let us call them u. Already we know u star and minus 3 is the root. So therefore u conjugate and minus 3, these are the roots. So therefore z minus u conjugate and z plus 3 will make it 0, isn't it? These are the three roots of this equation, right? Of this equation. So equation will be like this. Now when you simplify, it will be z cube, z square, z and 12. Now if you look at this equation, given equation, it also has the same coefficient. See, 1, so it is 1 here, 5, so it is 5 here, 10, so it is 10 here, and 12, so it is 12 here. So it means instead of descending order, it is in ascending order, right? So since coefficients are same of 1 plus 5w plus 10w square plus 12w cube is equal to 0, has same coefficients, therefore so what we will do, instead of z here we will write 1 minus u into w, 1 minus u conjugate into w, okay, and 1 plus 3 into w is equal to 0. When you multiply and open it, you will exactly get that equation, okay. So therefore from the first root, 1 minus u into w is equal to 0. So this gives you first w1 is equal to 1 by u. Then from this equation 1 minus u conjugate w is equal to 0, you get w2 is equal to 1 upon u conjugate, and from this you get w3 minus 1 by 3, right? So these will be the roots, okay. So that means let me copy it there because I have to write their values. How should I copy? Move it down. Let me move this down so that I can plug them together. Yeah, now I'll take them there. So therefore now look here, w1 will be what? 1 upon u. U was what? Look here, u we already wrote in Euler form, okay. Where is that a part? Look here, u is already there in the Euler form, right? So I'll copy this and then 1 upon u I will write. So 1 upon u means see, this was Euler form, right? U was like this in Euler form. So 1 upon 2 into e raised to that 2 into I raised to 2 pi by 3. So this will go up and it will become half of e raised to minus I 2 pi by 3, right? This, let me shift further. This was u. So this is the first root. Then w2, second root 1 upon u conjugate will be 1 upon 2 e to the power negative I, because conjugate will be change in sign, right? The first one was, first one will remain negative, second one will become positive when you take it up. Okay, let me erase this thing so that you are not confused. So is equal to half e to the power I into 2 pi by 3. This is second root, and w3 minus 1 by 3. Okay, already we got minus 1 by 3. So therefore, let me put them in boxes. First one, second one, and third one. These are the roots, right? So this is the answer for the roots. Are the roots of what was that equation? Okay, so this part we have completed, right? Now next part we have D part. It says consider the equation z square is equal to 2 into z conjugate. Z square is equal to 2 into z conjugate, where z belongs to a complex number. It is a complex number. By expressing z as a plus bi, find the roots of this equation. So z is equal to a plus bi. Therefore z conjugate will be a minus bi, right? And z square will be a plus bi bracket square, which will be a square minus b square plus 2abi, right? When we open the bracket square, right, it will be like that. So real part and imaginary parts are already separated here, real part and imaginary parts, right? Okay, now z cube, what is given? Z square. So therefore z square means this, a square minus b square plus 2abi is equal to 2 into z conjugate. Z conjugate is a minus bi, which is 2a minus 2bi. Comparing real and imaginary parts, we have, see, this real part is equal to this real part, and the imaginary part is equal to the imaginary part. Okay, so therefore a square minus b square is equal to 2a, and 2ab is equal to minus 2b. 2 and 2 gets cancelled, b and b also gets cancelled, so a is equal to minus 1. This is the value of a. When we have this value of a, so what will be the value of b? So a is minus 1, so minus 1 is square. Here I am putting minus b square is equal to 2 into minus 1. So this gives me 1 minus b square is equal to minus 2. So b square is equal to 3. So b is b is equal to plus minus root 3. So we have to find the roots of the equation. Okay, so therefore roots of the equation are See, a is minus 1 and b is plus minus root 3, which is the imaginary part. So, roots of the equation are minus 1 plus minus root 3i. That's it. Okay. So, with this we end this question. Okay. So, this was not difficult question. I hope you enjoyed it. Okay, in the next lesson I am going to teach you mathematical induction. It is very simple. Proof of mathematical induction, proof by contradiction, and use of counter examples to show that the statement is not always true. Okay then, I hope you enjoyed my lesson, right? Please like, share and subscribe my YouTube channel so that I get encouraged. If you have any doubts, please ask me on my email ID or on my WhatsApp. This PDF, the link of this PDF is given in the description of this video, right? Okay then.